So this would be the lecture part of the ligand discussion, and then after lunch, I think we're having a short tutorial. So, what are restraints and ligands? I mean, ligands are things that are non-standard protein or RNA, DNA, and for that you need to have new restraints. What are restraints? Well, they're mostly harmonic functions that provide chemical information to the refinement program so that it can decide what's a good bond, what's a good angle, and everything like that. And they're needed because macromolecular protein resolutions, you don't have enough data for the number of parameters in your refinement. And they're weighted against the experimental data. So if you have less experimental data, the geometry gets weighted up. If you have lots of experimental data, the geometry gets weighted down. And that has some consequences that are not easy to foresee. So for instance, at ultra high, you don't need them at all. At high res, you're going to have, if the restraints are good, you're still going to have large deviations because the experimental data is specific to the specific model you have. So you'll often see large deviations from restraints at high resolution. And then at low res, everything should approach the ideal values. If it's not approaching the ideal values, then you have something really squiffy in your model, and you need to do a lot of rebuilding, like large scale problems, like you've got things going backwards and whatnot. So if you have a low res model and you don't have very close to ideal, you have big problems. So in your refinement, there's lots of ways you can get restraints. There's libraries, and we have a monomer library, a very cut down version now, and a geostandard library, which is what I call the library that I have developed so that you can do less generation of restraints, and I'll talk about that. And there's also algorithms. So, when you have a protein, you have polymers, and each amino acid is lined up in your model, and we don't have a restraints file. We have a restraints file for, say, the first alanine and the second alanine, but there's not really a restraints file that you need to have for the connection between those two. Those things are in a file, but it's not the same library or concept. And so polymerization and linking of covalent ligands and other links like carbohydrates all need to be done algorithmically to make it easier for the user. Unfortunately, we can't do everything, so you do have to sometimes provide things yourself. Now, the geostandard has all of the standard amino acids, and it has also got all of the non-standard amino acids, and the same goes for nucleic acids. Standard and non-standard is there. Now, the geostandard, and I gave a talk on this a couple of days ago about there's 34K entities that have been Mogul validated in using this level of quantum chemistry, and I'm going higher as well. So that means that less and less, as soon as an entity gets put into the PDB, it goes into the Ligand Expo or something like that, it will be calculated, the restraints will be generated, and it'll be validated with Mogul. So there's going to be less and less use of generating restraints for some of the more standard things. However, if you're doing ligand studies, you'll have to do things to do so. And what that will mean is when you're trying to do a refinement in the GUI, this window will pop up. And it tells you there's a ZOZ, one entity, it doesn't have restraints, and it's telling you to perhaps run ready set. Now, ready set, I'll talk about later as well. And if you're a power user and using the command line, this is what you'll see. It says the number of atoms with unknown bonded energy types, 21. It's just the first error that comes up, but it's basically saying you need restraints. So when you see that, think restraints. One of the things about files is that they have a format, and the other thing about files is that they can have different pieces of information in the same file format. And crystallography, and then cryo-EM is coming soon, is all the files will be in CIF format. So it stands for crystallographic information file. MMCIF has macromolecular CIF information, and that's being used for all of these things. One confusing thing about ligands is that there's an information CIF file that you download from the PDBE. So you can go there and it gives you all of the information about the ligand. Unfortunately, it's not restraints. You have to use Elbow, which is the program in Phenix for doing this sort of thing, to generate restraints. So don't be fooled by, I found a CIF file on the PDBE and I've downloaded it. Why doesn't it work in my refinement? It's because it's not restraints. So I also recommend that you don't use the word CIF to define a file, because everything is going to be CIF very soon. So you should say restraints, model, data, and information, things like that. So what are restraints in more detail? For our purposes, we're going to talk about bonds, angles, dihedrals, chirals, and planes. There are more, but in the sense related to ligands, those are the ones that we're interested in. So these are the tools that are in Phenix that you can use. ELBO stands for Electronic Ligand Builder and Optimization Workbench. It's got a lot of things in there. It has so many things that can be overwhelming, and that's why there's two GUIs. One is a simplified wizard type GUI, and it will let you answer some questions, and then you get to that last screen that looks like every other GUI page in the GUI. Ready Set is a program that tries to take the model that you have and do everything that you need to start refining. And Ready Set is a game that kids play in Australia. It's Ready Set Go, and so everybody runs when they say go. So it's the same thing. You ready set and then you refine. It will generate restraints and things for you. And the Real is a restraints editor. So you can, if you're not happy with the restraints that you have at hand, and this can happen specifically for covalent ligands and really interesting moieties, you can change them a bit. So Elbow was written a while ago, and it's designed to make this tedious job easier. And it takes any chemical input and creates the two files, restraints and coordinates. And then you just need your protein and your reflection data to go on to refinement. The list of entities is broken into this information, and in the CIF format for the information about ligands, it contains smiles, atom names, and bonds. And I've already said not restraints, but these are the three things you really need. You need the atom names, because that's part of the mechanism whereby refinement looks up what your atoms are and what it's going to add a bond between these things. So that's really the information that's in the chemical information CIF, not restraints. Here's a picture of amino acid, alanine. I should point out that 5-letter codes appeared at the end of last year. So if you, I see some size. The first one appeared in December, so almost a year ago. And I had to retrofit my code to do it, because restraints are a big thing. I mean, ligands are the ones that are getting the 5-letter codes. And we've also retrofitted Phenix. So if you see a 5-letter code, it's almost certainly going to be a ligand, a new one. There's no 4-letter codes. They're sticking to 5-letter codes. So far, every single 5-letter code starts with A1. So if that comes up, I'm working quickly to make sure you don't even have to generate the restraints for them. So in Elbow, like I said, it's a workbench. And so you should throw everything that you know about your ligand. And the more you know about your ligand, the better your restraints are going to be. So to the left, you can see that if you just have the XYZ coordinate file, it's a chemical impact style, there's very little information. And then you have to try and figure out, I mean, the code, sorry, has to try and figure out what connections there are. And auto connections are not perfect because of the different, if you have a six-membered ring, is it aromatic or is it not? And you can't rely on the flanarity of it to intuit those sorts of things. So PDB is not a great input unless it has connect records and it has its hydrogens. So I suggest that you try and find out as much as you can about your ligand, and that would include a 3D mol 3D file, which has the 3D coordinates in it. A SMILES string has all of the connectivity, all of the element information about it. And the CCL, which is what I'm abbreviating, the chemical components library, that is a code which looks up the information in the chemical component library and uses all of that information in the chemical information CIF file to generate the restraints. So it's just a way of saying, oh, I want the restraints for ZOZ, with the example right at the beginning, and Albo will do that. And of course, the other thing that happens between a mismatch between your model and the restraints is the atom names. As I said, you have to have the right code and the right 3-letter code, 5-letter code, and the correct atom name so it can find it in the model to do things. So once you've generated all of the restraint objects and you've generated a 3D thing, you can then try and optimize the geometry. So you can either take a geometry that you like, you can ask Albo to calculate it using a simple force field, or there's an AM1 method that's in there, or you can even connect to outside programs like Orca is a open source quantum chemistry package that will give you a nice geometry. And in the Python 3 versions, which are coming the default soon, if you install the Python 3 version, it comes with MOPAC, which is another quantum chemistry package. After you've done some optimization, you will then get the restraints. So you're getting ready to define, you've got your restraints. If you don't want to do Elbow, you can ask ReadySet to do that for you. And it really just goes through this list of things. It adds hydrogens to your protein because we always suggest that you add hydrogens. It improves your clash scores. It improves the general geometry. So, people argue about the value, but anything better than 3.5 angstrom is a good time to have hydrogens. It optionally adds waters it optionally protonates water, and it also, for neutron refinement, takes care of some other, adding deuteriums in different forms. So what you get, restraints in a CIF file, and then it also converts link records in PDBs. Phenix doesn't honor link records, but it will convert them to edits. And so you can then optionally add the edits to your refinement. And it also adds, generates coordination libraries for metals, which is another important thing. And then if you are using ReadySet or not, and you want to edit the restraints, Real is a graphical user interface that comes with Phenix, and you can use it to generate geometry if you just load the model, and you can click here and there and do things like look at your model. Look at your ligand and look at the restraints. And if you want to change a value, you can do that. For instance, this is just a bond restraint and between these two atoms. And if you want to change it from 1.51, you can change it to something else. Ligand fitting. So now you've come to the next step. You have your ligand, you have a model, you have your 3-dimensional coordinates, you have restraints. You can fit it into that blob of density that's sitting there, and you don't know how well it's going to go. So there's a ligand fit program, and I was going to demonstrate that in the tutorial, unless people have other options, because there's a few things I can demo. It chooses the largest, biggest blob, breaks the ligand into pieces, tries to do a Fourier transform fit into those pieces, and then starts growing it from the core. And then it traces it out. And so this is a graphical representation of that. Pieces are taken. The largest one is wiggled in the blob, and then it grows out. And this has been working very well for quite some time, and it works at different resolutions. Here's some examples of fits that have worked at high and low res. This is really just a reiteration that link records have no impact. We try to automatically do the link records linking, and there's a parameter like link all equals true. It's currently set to false because we think that there's some linkings that you have to take a closer look at. So if you want to link ligands, I think that's currently off by default, but you can take a look. It's automatically doing carbohydrate linking, and it tries to do some metal linking. So for instance, zinc fingers are all automatic, and a few other metal types are automatic. There's nucleic acid restraints. So if you have RNA or DNA in there's base pair hydrogen bonding, base pair planarity between the two, because they should be planar, and then there's stacking. So that between each base pair, that should be done. The secondary structure restraints, as well as custom bonds and things. One important thing, the last piece of information there is that all of your information for any restraints that you ever do in your refinement is written to the geo file. And that is automatically written at the beginning of your refinement. So if you are doing something special and you look in Coot and you can't see a bond, that is not confirmation that it is or is not there. You have to go to the geo file to prove whether it is or is not there. Because Coot is just doing its best to do what, to show you something. The only thing that is the gold standard is this geo file. So we're currently working on a GUI to show you more information about that. But right now, text editor in there looking for the bond or angle that you're interested in. So this is just a cautionary tale. If you're taking a model and fitting it into a blob of density, like we've been doing all morning, make sure that the waters and ligands, if they're taken across, are actually there. Because if there's a ligand in the model that you're fitting into your cryo blob, doesn't mean it's in your cryo blob. It was in the other one. Okay, so to check whether this ligand is there, you can do emit maps. We have a thing called a polar emit map. It is a very, very powerful way of testing. Unfortunately, it's only X-ray, of course, whether your ligand is really there, because it checks if it takes it away, we don't let the bulk solvent roll in and flood the density case. So this is your friend when you're trying to prove that it's there. I have also updated and made more powerful the way that you can create restraints. There's if you're doing restraints with elbow, you're doing it in isolation or in a synthetic water bath. However, this allows you to, it's called QM restraints, because it calculates using the quantum chemical level of theory in situ. So if you say I have a ligand and it's in my protein, what the program does is it takes the ligand and a sphere around it, puts it into QM, freezes the protein, lets the ligand move, and generates restraints for that particular orientation. So you're having a much better set of restraints, firstly because it's QM, secondly because it's in situ. So you're getting much better restraints. You can, if you get the Python 3 installer at the bottom of the download page, it's already in there. It's distributed with, because we couldn't distribute it with Python 2, but Python 3. So if you need that, you have to install that one. And basically, you can see here, this is just a visual representation of what I just said. This blue ligand in the protein model is taken out, and the pocket around it is included in the QM calculation. And then you get a minimized geometry and the restraints. And you can do that either standalone beforehand, and beforehand you just do it at the command line, unfortunately, right now, or you can run refinement and provide the refinement with a fill file, and it will do it inline in the refinement. So you don't have to do it separately if you don't want to. You can do it separately to check that everything works fine, and then once you have your fill file, you can run it every now and then when you're doing a refinement, or every time. It doesn't take a very long time. And so this is a toy example. It's just toluene, and you can see that it hasn't moved much because I've got the input and the refined model superimposed, but it's showing you that it doesn't change much, which is good. In this case, you wouldn't expect toluene to be a very flexible or poorly defined model ligand, but it does show you that there is a hydrogen bond connection here with a sulfur just off the page. And here's an example of how if you calculated it in isolation, this is the conformation that you get. This ring here is in one pucker, but if it's in situ, it's in a different pucker, and you're going to get different bonds and angles. So it improves the relevance of the restraints. And then one other thing is, how do you tell which histidine protonation do you have? So what I do is I use the similar program mechanism for what I was just showing you, and I run 6 different histidine calculations to see which one is the best. Everything else is frozen, but the histidines are put in and minimized. And then you can compare the energies, which is the first column, or the second column is the delta energies. And you can see that the second one with only HD1, the delta 1 on the nitrogen, is the lowest energy. So that is your answer. And you can see that that's why this is the answer. The histidine is coordinated with the water up there. And then the other cool thing is that you can see different different hydrogen bonding networks. So the one on the left is a very close second to the one on the right. But it's only because the orientation of the water, you're getting one is donating and one is accepting. So summary, and I seem to be pretty close to time. You can use elbow and ready set to get restraints. I didn't say it at the time, but it's garbage in, garbage out. So please get as much information about your ligand as you can. Otherwise, you're just going to get garbage. Hopefully, you have better experimental data than your restraints in that case. You need to know as much about the file, and always look in the geo standard, the .geo file, if you have any questions about the restraints. Coot's not going to show you, Chimera's not going to show you. Until we have the GUI that comes with Phenix, you're not going to know. So thank you.